Alright, so today I'm gonna be explaining another important article, and the title is Latent Domain Generation for Unsupervised Domain Adaptation Object Counting. This paper in 2023 from IEEE. Unsupervised cross-domain object counting has recently received great attention in computer vision, which generalizes the model from the source domain to the unlabeled target domain. However, it is an extremely challenging task because only unlabeled data is available from the target domain, and the domain gap between the two domains is implicit in object counting. So in this paper, we propose a latent domain generation method to improve the generalization ability of unsupervised domain adaptation object counting by generating a latent domain. So we are generating a latent domain. So we propose a domain generator with random perturbations to learn a new latent distribution derived from this original source distribution. The latent domain generator can extract target information sampled in its stochastic latent representation, which preserves the original target information and enhances the diverse ability. Meanwhile, to ensure that the generated latent domain is consistent with the source domain in counting performance, we introduce a consistency loss to encourage similar output from latent and source domains. Moreover, to enhance the adaptation ability of the generated latent domain, we apply the adversarial loss to achieve alignment between latent and target domain. The domain generator with the adversarial loss and consistency loss ensures that the generated domain is aligned to the target while also improving the robustness of original source domain model. You see the overview of our proposed latent domain generation method. We have domain generator here. So it receives a target domain and a source domain, and it creates feature generator. Then we have this density decoder here. And domain generator uses the autoencoder to obtain a generated domain. Adversarial discriminator learn the domain invariation between the generated domain and target domain. This density decoder here decodes the final density maps. To empower these blocks, there are three training losses. The first one is supervised loss. The second one is consistency loss. And the last one is adversarial loss. The supervised loss ensures feature generator and density decoder for counting is accurate. The consistency loss ensures the model is robust to data in both source domain and generated domain. And the adversarial loss that encourages the generated domain to align to the target domain. So X sub S represents a labeled dataset from source domain. K is the number of samples in the source dataset. M is the number of samples in the target sample. So TU represents the task of unsupervised domain adaptation. There are some network components. For example, G, let G be a domain generator, which is function parameterized by theta G, which maps an image to a generated representation. Let F be a feature generator parameterized by theta F, which maps an image to a hidden representation, representing features that in a high-level dimension. Let D be a discriminator, making the features from the two domains have a similar distribution. Finally, M represents a density map decoder parameterized by theta M that maps from hidden representation to the density map prediction Y. The autoencoder is used to reconstruct the high-dimensional input vectors by low-dimensional codes. You see in picture, G is our proposed latent domain generator. Each source domain will be transformed into X sub hat with the target information, which represents the new generated domain image. So this is an image, this is a generated image, and Q is the latent representation that you know in autoencoder, in variational autoencoder. To extract target information, increase diversity of target information, we use the sample operation, which is implemented as the reparameterization trick in the sampling process. Z is the latent variable. Our method is to sample the stochastic latent representation and to encode these for the original source domain to obtain a new latent domain sample. So with our latent domain generator, the generated new domain can maintain the source information with the stochastic target domain characteristics. First, the newly generated domain can improve the robustness of the model by the supervised loss and consistency loss in the source model and consistency module. So the stochastic sampling in extracting target characteristics can greatly improve the diversity of the newly generated domains, thereby improving the robustness of the model, while also preserving the original target characteristic. Second, in the adaptation module, it is more feasible to narrow the distance between the newly generated domain and the target domain, and rather than directly narrowing the distribution of the two different domains. So these are the details that, inspired by this idea, we feed our original source domain input and the generated domain input to the supervised counting model, and we propose to employ consistency loss to ensure the output of the generated domain is consistent with the original domain. And here is just the total pixels. Each sample goes through this feature generator and this density decoder M. Density decoder feature generator. And then about learning cross-domain similarity. Well, to align the generated latent domain with the target domain distribution, we propose an adaptation model with an adversarial loss to learn a similarity between the generated domain and the target domain. The disturbed source image for a source input image is defined in 2 as the output of an autoencoder. So followed the unsupervised domain adaptation framework based on adversarial learning. The proposed model consists of 3 parts: domain generator, feature generator, adversarial discriminator. So we introduced the training step for adversarial loss, the generator step for training generator, and discriminator step for training discriminator. For the generator, there are 2 generators in this step: the feature generator and the domain generator. So we usually have feature generator, but this domain generator, this one is new in this paper. This is the novelty of this paper, to ensure the consistency for the feature generator F and the density map decoder M of F. The consistency loss is crucial to ensure output's consistency between the generator samples and the corresponding source images. Then adversarial loss fools the discriminator by maximizing the probability, and you know this adversarial technique. What about the discriminator? In discriminator step distinguishes whether the input is from latent source domain or target. So even this one is standard. So this is the algorithm. We have construct the consistency loss, adversarial loss, supervised loss, and so if a step is generator, we compute this loss. If a step is discriminator, we compute this loss. So in the discriminator, I don't see any consistency loss. Yes, because we don't have autoencoder at that moment. So you see, counting is very interesting. Counting the people, counting heads. And it's very challenging. For example, when I'm a class assistant, when I count heads, I always have problems. But they can immediately count several heads. You see, Shanghai Tech Part B, Shanghai Tech Part A, different image, different data sets. And it can be seen that each data set all has multiple densities, multiple scales, different scales, and complex background issues as well. And you see the unsupervised cross-domain object counting. You see first images, then ground truths without adaptation, and then without adaptation with contrast 90%.